Well, welcome everyone. So it's a pleasure having today Professor Licia Verde. So she's in the island for different reasons, but she kindly accepted visiting us during the day. So she will be here only today and giving us a talk. So probably most of you know her, but well, just to give her an introduction about her CV and career. Licia was an undergrad at Padua. Correct me if I make any mistakes. So she undertook her PhD at the Institute of Astronomy in Edinburgh. She defended her PhD in 2001, and she was involved at the time in the 2DF. Mm-hmm. So she was the leading author of one of the 2DF Galaxy Redshift survey papers that came out of this collaboration. And then in 2001, after she completed her PhD, she moved to Princeton. She then became involved in the WMAP collaboration. She was the leading author of one of the first year data release WMAP papers. It's a highly cited paper in the area. Then she moved to Rutgers in 2002, 2003. And then she moved back to Princeton with a Chandra and Spitzer fellowships. And then she got a permanent position, a faculty position in UPenn, where she stayed until 2007. Mm-hmm. And in 2007, she came to Spain, to Barcelona, where she is holding an ICREA professorship. And since then, she's been involved in different cosmology projects. She was involved also during her stay in the United States in ACT, in the Atacama Cosmology Telescope. And more recently, she's involved in BOSS collaboration. Also, she's involved in DAISY and Euclid. And today, she's going to tell us about beyond precision cosmology, some examples. So please, Licia.
Thank you.
Okay.
So thank you for this introduction. And maybe you know, or maybe you don't know that when I ended up in Edinburgh, because I asked to do my Erasmus exchange actually here in Canary Island, and then the Erasmus coordinator looked at me and say, you will be having fun and partying all the time if I send you to the Canary Islands. So I send you where it rains all the time in Scotland, and you'll be studying, and at least you can finish your degree. And he didn't know that the weather is also bad here. But so so this is what I want to talk about today. So in the first decade of the year 2000, so the establishment of what we call precision cosmology, thanks to a massive observational effort, and some of the survey are mentioned there. And as a result of this effort, we now have a standard cosmological model, which is the famous or infamous Lambda CDM model, where the universe it's dominated by a cosmological constant, and then the matter content is dominated by dark matter. In this model, we have just 6 numbers, 6 parameters that describe the universe composition and evolution as far as the observation we have can tell us. And some of the parameters describe the homogeneous background, mostly the composition of the universe and the current expansion rate, and some parameters describe the perturbations, mostly the primordial power spectrum is assumed to be a power law. So to give a context and overview, in the past 20 years, we've made the transition to precision cosmology because these numbers are now known with % precision. The standard cosmological model needs a very few parameters, but there is a very fundamental difference between modeling and understanding, and this implies challenges and opportunity. And on top of that, cosmology is special because we can't make experiment like you do in other branches of physics. Although we call them experiment, what we really do are observations. We just use the entire universe as a detector. We just observe the detector and extract information from that. But the detector is given and we can't tinker with it. So the name of the game has been to basically observe as much as possible as you can of the universe, and that's what we have been doing, especially over the past 20 years. So In particular, we should remember that with the latest release of the Planck, the latest Planck results and the satellite, basically the information content of the primary cosmic microwave background temperature anisotropies has been saturated. I mean, we have observed really all that there is to observe. So we've performed as a cosmologist, not me, I'm not involved with the Planck collaboration, as a cosmology, the ultimate experiment, that's it. And in the field, this is not the case for the polarization. We know the CMB light is also polarized, but this is an example of that we can do ultimate experiment. And in the field of large scale structure, that is studying the large scale distribution of galaxies and inferring the matter, we are not there yet, but in principle, we could get to the limit of actually observing all there is to observe and arrive to, a statistical error floor. What does this mean? This means that we can now do precision tests of fundamental physics by looking at the cosmological data. So mostly, this is done by taking some base model, which is the 6-parameter lambda CDM model, adding 1 parameter at a time and trying to constrain this parameter, and this parameter is supposed to be or parameterize some deviation from this model. So this is a little bit similar to the situation of particle physics in the 70s, when the standard model was established, then precision test of the standard model started being proposed and developed, and people were looking for small deviation from the standard model, but by the way, we are still looking for small deviation from the standard model. So as a result of all this huge experimental effort that went on, and here people also were involved with the Sloan survey, with the BOSS survey, so you all know what it means, with the Planck satellite and so on. As a result, we still have a wonderful agreement of all this new data with this lambda CDM model, with some notable exceptions that are still up for discussion, and I'm going to discuss about at least one of these. So the question that we should ask ourselves is this the whole story? So we still don't know what 96% of the universe is. We don't really know what set out the primordial perturbation. The model is really preposterous because we have a cosmological constant that we don't really know what it is, and this, of course, implies challenges and opportunities. But in my view, it goes probably even deeper than that. And it goes as follows. This is what Daniel Kahneman says about theories. We can't live in a state of perpetual doubt, so we make up the best story possible and we live as if the story were true. And in cosmology, we have a lot of stories. General relativity, which we've tested on solar system scale and we apply on horizon size scales. We made the extrapolation of, almost 13th order of magnitude. The Big Bang, the choice of metric, nucleosynthesis, etc., etc., etc. So cosmology tends to rely heavily on models, both for the signal and for the noise. But we know that essentially all models are wrong, just some are useful. So as we are observing larger and larger volume of the universe, and as we are shrinking the statistical error at the percent level, we are reaching the percent precision, then systematic become the name of the game. And by systematic, I mean anything that is a shift between the true value and the value you report within the error bars. So I mean not just systematics in the data, which have been around, have been discussed for very long, but also systematics in the model and in the analysis. So given that cosmology relies so much on models, my question is, can we do things that are a little bit less model dependent and see what we can learn about the model itself? And now I think this approach is a bit still in its infancy, so I'm sure you saw an exploratory example of some of the work that I've done with my collaborator, mostly in the group in Barcelona, over the past year or so. And so, depending on the time, I'm going to discuss these 3 papers. One is called The Trouble with H0, and I would like to highlight the work of PhD student Jose Luis Bernal. The length of the local standard ruler, and some way to constrain early cosmology, and I highlighted here the work of the postdoc Emilio Bellini there. So let's start with the first one, The Trouble with H0. So we have, over the past year, a direct measurement of the local expansion, the present-day expansion rate of the universe, the Hubble constant, which is, here it is, 733.24 plus or minus 1.74 kilometers per second per megaparsec. This is a direct measurement. It's done using supernovae, using Cepheid, using parallaxes, and so on and so forth. And Adam Rees and collaborator not just produced this measurement, but also recently verified with the newly released Gaia parallaxes that the parallaxes they had done with HST by scanning the instrument along the line of where the CCD was being read out to get a better measurement of the parallax was actually correct. And so this holds. However, we also have recent the Planck data release with the analysis, and in a lambda CDM model, what the Planck data says is that this number should actually be 67.8 plus or minus 0.9. If you include the polarization, it's the same, but with the error bars slightly smaller. So formally, the difference between these two numbers is 3.4 sigmas. Now, of course, for particle physicists, we should really pay attention when it's 5 sigma. In cosmology, we don't have the luxury of the 5 sigma, and I think for a fundamental reason, which in our error bars, we always include cosmic variance. So we don't want to measure what is the value of the quantity in the patch of the universe that you observe, but we also want to include the error that you have due to the fact that there could be an whole ensemble of all the universes that are drawn from the same initial condition and for the same model. So that's why we are happy with 3 sigma and not 5 sigma. But anyway, so in cosmology, 3 sigma is the golden rule, not 5, and this is 3.4, so maybe we should pay attention to that. Now, gets probably worse with the new reanalysis of the Planck low L polarization, but those that are not in the collaboration don't have full access to actually do this test, but we know that it's 3.4 or worse, so we should pay attention. So what's the landscape? Let me summarize. So this is the measurement of H naught. Here, this is the direct measurement coming from Adam Rees and collaborators. And these are various combination of cosmic microwave background data. This is WMAP, this is Planck. This is Planck with baryon acoustic oscillation or with lensing larger scale structure, and various combination with or without polarization. This is in a lambda CDM model. This is what happens if you allow for an extra, so a free number of effective neutrino species, which doesn't necessarily mean that you have an extra 0.3 neutrino or 0.4 neutrino. It just simply means that you are allowing some freedom in changing the early time expansion history of the universe, which then you parameterize as some effective degree of freedom. And this is what happened there. And these green error bars come from a very recent measurement from the time delay distances that were released this fall. So these are the Shuyu and collaborators, the Holy Cow collaborators of the time delay distances. Okay, so if we take this 3.4 sigma seriously, then we should discuss and see what's going on there. So what we decided is to take 3 avenues without invoking systematics, beside those declared by the author themselves in print. So you can always say, I don't believe the H-naught measurement because it involves Cepheids and exploding stars, and we don't understand the exploding stars. You can try to play that game, but I don't want to play that game. The game I want to play is I just take whatever is published and consider the systematic that the author themselves say there could be a systematic here. And then follow 3 avenues. Either allow the early cosmology to deviate from the lambda CDM model and leave unaltered the late time cosmology, or give some freedom to the late cosmology, leaving unaltered early time physics. And here I put an asterisk because what I will also try to do is to maybe relax this and also leave some freedom to the early time physics as well and see what I can do. And then I'm going to try to do it in a model-independent way. So these are the data that we'll consider. For the cosmic microwave background, we consider the Planck 2015 or 16 release, temperature, polarization, lengthing, and we'll maybe consider there was a paper by Addison and collaborator by splitting the Planck data at low L, lower than 1,000, multiple of 1,000 and higher than multiple 1,000, and they found some sort of mismatch there. But the compilation from the baryon acoustic oscillation, the standard golden combination that everybody use. Now, if not everybody is a cosmologist here, do you know what the baryon acoustic oscillations are? Yes, no? Okay, in briefly. We were able to learn a lot about cosmology from the cosmic microwave background, basically because there is a fundamental lens in the cosmic microwave background is the sound horizon at recombination, and we see that through the entire history, distance, and geometry of the universe. And so we were able to determine composition and geometry of the universe because of that. But the limitation of doing this is that the cosmic microwave background is at a given redshift, and so we could only take one snapshot of this. However, what we're seeing in the cosmic microwave background is the photons that were coupled to the baryons in these acoustic oscillations, and then a recombination, the photon traveled to us and give us a snapshot of what's going on there. But let's consider that the baryons are about 1/7 of the dark matter, and the baryons have mass. And so if the baryons were participating to these acoustic oscillations, and they had mass, also the dark matter should have felt that something was going on. Right? And so as the baryon are coupled to the photon, if you can imagine on a single perturbation, the photons go and travel with the baryons until the recombination, and then the photons travel to you, and you perturbation or baryonic perturbation find yourself displaced with respect to the dark matter perturbation. You have mass, but the dark matter has mass, and you know gravity works both ways. So it's true that the baryon tend to fall into the dark matter potential well, but also the dark matter tend to fall into this displaced baryon potential well. And so you will find a shadow into the dark matter distribution of this fundamental length that we saw in the cosmic microwave background. Now that's in the dark matter, but eventually stars and galaxies will form on this scaffolding created by the dark matter potential well. And so now in the galaxy distribution, you should be able to see that same feature. Now, to be precise, it's not the sound horizon at the last scattering surface, it's the sound horizon at radiation drag, but you know, it's still a standard ruler. But now you can play the game of the standard ruler not just at a given distance, which is the distance of the last scattering surface. You can play the game at several different distances because you can observe a larger scale structure from very close to you until we've observed almost to redshift 0.7. Or even beyond if we look at the Lyman alpha forest. Now, we don't consider the Lyman alpha forest here just because everybody uses this combination of data, and that's the same combination of data that we use, so we get to redshift 0.7 or so. And then the standard supernovae, the JLA compilation, and we all know supernovae are standard candles, and they give you some DL, luminosity distance. So these two measurements are measurement of the expansion history of the universe. This we all know is the cosmic microwave background, and this is the recent collaborator Hubble constant measurement, which we go back to the beginning. So here it is. Supernova are standard candles. They have an intrinsic luminosity, which we believe it could be standardizable at least. This luminosity, it's poorly known, so these are some uncalibrated distance measurement, but they all have more or less, they all have the same, or they can be standardized to have the same intrinsic luminosity, so supernovae can give us a luminosity distance, and any metric theory of gravity relate the luminosity distance to the angular size distance, and what the baryon acoustic oscillation tell you, it's related to the angular size distance. So since the intrinsic luminosity of the supernova that goes there, it's poorly known, this is called this is uncalibrated, and usually calibrated, for example, using measurement of H0. This is what I was saying about the baryon acoustic oscillation. The physics, it's the sound wave in the early universe propagate until radiation and matter decouple. This imprints a scale at standard ruler, which is a key observable, is useful to determine the geometry of the universe, but the early universe and physics sets it. So this is also a probe of the expansion history of the universe. So the way this distance is, the way to probe the expansion history of the universe with the BAO, it's also uncalibrated by itself. It gets calibrated on the cosmic microwave background, because the cosmic microwave background tell us what the length of the standard ruler is. And in the lambda CDM universe, this standard ruler length is known to 0.2%, which is an exquisite measurement. The cool thing is that we can observe these two, standard candle and standard ruler, now over the same range of redshift. So type 1a supernovae measure relative distances because there is an uncertainty in their magnitude. The baryonic acoustic oscillation measure absolute distances if you know the value of the sound horizon radiation drag as set by the cosmic microwave background by the early universe physics. Here are the measurements in their full glories. These are the BAO measurement, and these are the actual supernovae measurements. Visually, in a cartoon way, what I want to show is the following, and I want to introduce a concept which I call the direct and the inverse distance ladder. So here we have H0, a direct measurement from Riese collaborator, which is centered at low redshift. It's around 0.04 effective redshift and so on. And then we have the supernovae, which goes from very low redshift to just above redshift 1 to measure the expansion history of the universe. Then we have the baryon acoustic oscillation, which most of their statistical power is between redshift 0.1 and 0.7 or so. And then we have here the cosmic microwave background at redshift 1100, which give us the high redshift anchor, the sound horizon and radiation drag. So Hubble constant give you some low redshift anchor, the cosmic microwave background give you a high redshift anchor, but the high redshift anchor of the cosmic microwave background, it's given to the baryon acoustic oscillation, and usually, traditionally, the anchor for the supernova is given by H0. But now, since these two cover with high statistical power the same range of redshift, you join the two ladder. So you could build a ladder by using the low redshift anchor and going that way, or you could build a ladder by using the high redshift anchor and going instead this way. Okay, so we have the problem of the mismatch with H0. Let's try the first approach to modify the early universe physics. So let's see how we can modify the early universe physics and see if we can fix the mismatch. So the first thing that comes to mind is try to change the primordial helium fraction, because that changes the recombination history. It affects diffusion damping. It affects for the redshift last scattering. And that's one of the ways you can try to affect sound horizon radiation drag and therefore the infer value of H0. And so these are, this is the H0 measurement, the usual one. This horizontal line are different measurements. You can match the colors of primordial helium fraction from H2 region, from main sequence dwarf, from initial solar abundance, etc., etc. And these are the constraints from the Planck with high L polarization and without high L polarization. So in other words, the contour here don't touch, the contour here touch, but the moment you add baryon acoustic oscillation, the contour don't touch. So this is saying that this is probably not the explanation to explain the mismatch. What about if we try to modify the early time expansion history, and then the parameter of choice is the number of effective neutrino species? This doesn't necessarily mean that you are adding a fractional neutrino. It means that you are changing the early time expansion history, you are changing H at around recombination and before. So this is without the Planck high L polarization, and this is without a high L Planck polarization. So what this is telling you that, oh look, if you add about 0.4 effective neutrinos, you can get agreement between what Planck says H0 should be and what Adam and Cepheids and parallax and local supernova tell you H0 should be. However, the moment where you add the high L Planck polarization, this possibility fades away because this contour get cut down there. So why do I keep splitting with high L polarization and without high L polarization the Planck analysis? But because if I look at the Planck paper after they went through the referee report, there is a claim that says, use the polarization within the lambda CDM model, use it at your own risk beyond the lambda CDM model. So I don't want to take any risk, and I'm going to show you the two cases. Okay, so far we've changed just this function history in the early universe. Can we also maybe try to play around with the perturbations and see if something happened there? So here we add two parameters of this extra fluid neutrino-like. We have a viscosity parameter and a sound speed parameter. So if all species have the same viscosity and sound speed, not much change, so there is no evidence for relativistic species not being neutrinos. But then we ask, what if you have 3 neutrinos plus something else which doesn't behave in the perturbation like neutrinos? Right? So they behave in the expansion history but not in the perturbation. And so these parameters now describe just this extra species. So this is something that has been called dark radiation, and you can run your constraints and you end up having some relatively large error bars, but still there's no much room for, there's no evidence for having something that does not behave much like neutrinos. The interpretation of these parameters is that whatever it is, if it is 1/3, 1/3, then you have a relativistic free streaming relic. This is the exact. If you have 0 and 1/3, then it's a relativistic perfect fluid. If you have instead of some sort of dark energy-like scalar field oscillating in a potential, then you would have 1 and 0. If the parameters are somewhere else, then this will be other dark radiation candidate, which parameter are just effective parameter. It's not, so it's some effective thing. So what happened in this case? This is again with the high L Planck polarization, without the high L Planck polarization. Yes, if you have some freedom to add some extra, to change the early time expansion history of the universe, and then you will sort of decrease the tension. The moment where you add the high L polarization, this possibility again fades away, and there's no much room for extra stuff like this. So here it is again. All right. So let's go on and instead try to change the late time cosmology. Bad luck with early time cosmology. Let's try the late time cosmology. So what we decide to do, let's say, well, let's try to do an S-spline reconstruction of the expansion history. Let's parameterize the expansion history like an S-spline. So we parameterize the Hubble as a function of redshift with 4 or 5 knots, because the moment you add supernova, it goes to a redshift a little bit higher than the BAO, so you have to put an extra knot there. The moment we don't introduce the supernova, just with 4 knots, it works. And then play around with this direct and inverse cosmic distance ladder. So reminds, this is the direct cosmic distance ladder, and this is the inverse cosmic distance ladder. So let me take an aside. So here is where in the lambda CDM or its simple variation, the two ladders don't match. So in the lambda CDM or simple variation, CMB tells you RS, you do this, and you get a different value of H naught that you would get by actually measuring the H naught. So let me do a slight aside, because I've been always saying you want to be model independent, etc., but when we look at the cosmic microwave background, which is what we look here to measure or get an estimate of the sound horizon radiation drag, in the cosmic microwave background, early time information and late time information are all mixed together, because we observe the cosmic microwave background through basically the entire universe. And so the position of the peak depends on the geometry, depends on the expansion history, how far away the CMB is. And so how can we say that we are trying to be model independent if maybe we are using the lambda CDM model to measure the sound horizon radiation drag? So I'm going to return to this later on, but there is a way to disentangle the early time effect and the late time effect in the analysis of the cosmic microwave background. And there is a way to extract the measurement of the sound horizon radiation drag in a way that is robust to assumption that you can do about the late time universe. I'm going to come back to this later on, but the answer is yes. And the answer you get is 147 plus or minus 0.34. So the error bars are not much larger than doing the analysis in the standard way. But let's keep this number in mind and then go on and then go back. So let's say that we use the H naught measurement, the baryon acoustic oscillation measurement, and the determination of the sound horizon done as I told you in this as I told you here, okay? And then try to reconstruct the expansion history in S-spline. So if you only use the baryon acoustic oscillation and you put both H naught and the sound horizon radiation drag, what do the BAO tell you? Oh, well, they tell you, so this will be the Planck prediction. This will be a lambda CDM model with an H naught, which is what Adam Rees will measure. And what this does is basically say, look, more or less within the error bar, it looks like a Planck lambda CDM, but then a very low redshift where you don't have BAO data anymore, this goes back up to match the measurement, Adam Rees measurement. Because remember, the bioacoustic oscillation have a lot of statistical power here, but have very little statistical power at low redshift because there's no volume to measure them. And these are the residual with respect to a lambda CDM model with where the data points are. Okay? So now instead, do H naught plus supernovae. And now what this does, it completely forget about what Planck tells you, because there's no Planck here, there's no RS information, there's no BAO. And it just follow a lambda CDM expansion history with the same value of Adam Rees H naught. Of course, you put that into the fit, and then at high redshift it does whatever it wants to do. And this is the residual. So if you put in BAO, to match H naught, it wants some late time increase acceleration, of course, where you have no data. The moment you put in the supernova, which sample very well the expansion history of the universe at low redshift, because we have a lot of supernova around redshift 0.1, then you don't want that anymore. And then you can try to put together both H naught, BAO, the supernova, and RS. And then what the fit does is say, look, the error on RS on the high redshift anchor is much smaller than the error on the low redshift anchor. So forget about the low redshift anchor. I'm going to fit the high redshift anchor. And all the data tells me is that I want a form that is a lambda CDM-like. There's no wiggle room. And so if you now forget about the high redshift anchor, it still gives you a lambda CDM shape, but matching the low redshift anchor. And so, and these are the residual compared with the BAO data, and these are the residual compared with the supernova data. So in other words, the shape of this function history is very well constrained. So here what we do the reconstruction of the shape, marginalizing over the anchor. Forget about the anchor, just tell me what the shape is. And the reconstruction of the shape of this function history has deviation which are not even 5%. Where you have data, of course. Where you start not having data, then the reconstruction goes crazy. The issue is with the normalization. So the H-naught problem can be translated into a sound horizon radiation drag problem. Since there is no much room to change this function history of the universe, then you have a mismatch, don't know where to anchor. So you can choose one anchor and then you have a problem in the high redshift anchor, or you can use the high redshift anchor, you have a problem in the low redshift anchor. So the first plot, you can alternatively show it like this. This is the sound horizon radiation drag determined by this kind of reconstruction, and this is the sound horizon radiation drag determined by the cosmic microwave background. This is a model-dependent measurement. This is a model-independent measurement. This is a model-dependent because in a lambda CDM you have almost 3 sigma discrepancy. If you allow to have an extra number of, a free number of effective neutrino species, then the discrepancy is not that big anymore. Now, why it is 2.8 while before it was 3.4? Well, because before it was a model-dependent fit. Now this measurement is a model-independent one. So the error bar grow and the significance is a little bit lower. So in a nutshell, the H-naught problem is an anchor problem, either a redshift 0 or a redshift 1100, which cannot be solved by tweaking or bending the function history. It can be solved by changing RS, those the early time physics, but polarization data impose tight limits on how much you can play around with this. But this is why there are being so much interest in the number of effective neutrino species, because this could not be neutrino, it could be an axion or anything that changed the early time expansion history. So this is the sound horizon radiation drag versus H-naught with the different measurement. Adam Rees measurement, Planck measurement, WMAP in a lambda CDM. This is Planck in a lambda CDM plus an effective. This is Planck in a lambda CDM without an effective. This with high L polarization, this is without the high L polarization. So that's why there are being so much interest into that, because this may actually solve the problem, but it's disfavored by the high L Planck polarization. Okay, so let's move on and say, okay, so this is telling me, you are telling me that you can measure the sound horizon radiation drag without the CMB. If you use H-naught, use the supernova and use the BAO, then you can infer what the CMB should measure for the sound horizon radiation drag without making any assumption about gravity or about dark energy, because I just parameterize this function history just as a smooth function. So this is very powerful, because we really like the baryon acoustic oscillation, because the theoretical prediction depends on the physics and recombination, and the measure depends on the cosmology at low redshift. And for example, some aspects of recombination physical set are very, very high redshift. So you can test a complete model with the data from all these very different epochs, if it all match. And if it doesn't match, then maybe you have a clue to check where things can be going on. So the question is, how long is the standard ruler? So normally when you measure it from the cosmic microwave background, you say this is the integral of the sound speed, so it's how far things can travel until radiation drag. And then, but what you measure angles. So most of what you can do with cosmology, with the baryon acoustic oscillation, you can also do it without knowing the length of the standard ruler, as long as you know it's a standard ruler. So the geometry can be measured with a standard ruler whose length is not necessarily important. But can you measure how long is the ruler in a model-independent way, so you can use it to test model? So we started thinking about this, almost 3 years ago. And this is similar in the philosophy of a paper from even 2 years earlier, but this paper was doing it in a completely model-dependent way, while we went into the model-independent way. So what you measure an angle, where the angle is the length of the standard ruler divided by the angular size distance, and you can get this from the Robertson-Walker metric, and this is the relation of the angular size distance to the element of the metric. So notice that I'm not assuming GR. I mean, this metric, you can write it in GR, but this is not GR. GR is telling you how stuff move. But this is just spherically symmetric and homogeneous. There is no GR in here, just symmetry. And there's no assumption about dark energy either, because I will just parameterize the expansion history in S-plane. So the assumption that I have to make, of course, are the existence of standard ruler and standard candles. So you don't need to use a model, just use the data. You use the supernovae, and you rely on the fact that any metric theory of gravity implies this relation between the luminosity distance and the angular size distance. Again, there's no GR here. And if you're really adventurous, you can also add another probe of the expansion history beside the baryon acoustic oscillation, which is what I call standard clocks. Now, I will not say more about this because we can do our argument even without the clocks, but let me just float the idea here. This is a series of references where this method was developed. The idea is that all elliptical galaxies have stellar population well described by a single age, and as you know, differential ages are related to the Hubble parameter as a function of redshift, which is nothing but the expansion history of the universe. Now, this expression ignores the spread information time incomparable to the Hubble time, so you can already say that this is going to work on redshift 1, up to redshift 1, not much beyond that. And of course, H0. So what are the basic model parameter and assumption? Assume only the cosmological principle, homogeneity and isotropy, so you can write an FRW matrix. The equation of state of dark energy is not assumed. A metric theory of gravity and some smooth expansion history, no cosmological model here. So late time data below redshift 1.3 or 1.8 if you use also some clocks tell us the length of the standard ruler. The physics of the early universe sets it. Let's see if we can compare them. So parameters. Ruler length, that's what we are interested in. Supernova magnitude, which marginalize over this at the end. The inverse curvature radius of the universe, so which is in units of H0 over C, 1 over the size of the observable universe, and then 1 over H at 5 or 7 different redshift depending on the data set we consider, and we linearly interpolate in between them. So just MC it and see what comes out. So to interpret the result, remember there are 2 ways to report the result for the standard ruler measured from the low redshift. If you only have supernova and baryon acoustic oscillation, remember you only measure relative distances. So you will measure the length of the standard ruler in this combination. It will be in units of megaparsec over H or RS times H. However, if you add an absolute measurement, either H0 or H as a function of redshift, then you can drop this little h from here and you can measure the quantity in the same unit as CMB will give it to you. So here are the results. Both assuming flatness and not assuming flatness. So here I report omega k for you to make the connection with the typical omega k, but omega k is GR, well, this is not necessarily GR. And now what I want you to focus on is the combination of supernova and BAO for this quantity in units of megaparsecs over H. This is a 2% measure. Now, of course, if you want to have it in megaparsec, then this error is dominated by the error on your anchor for H. So you need to add a measurement of H somewhere, and these are the combination you get. So now we want to compare this with the Planck constraint within a lambda CDM model. So let's say you take supernovae, BAO, and H naught, you get this number, the error is 4 point something, and this is more than 10 times smaller. But this is model independent, this is model dependent. The moment I drop the lambda CDM hypothesis, the moment I leave some freedom in the early time expansion history of the universe, this error bar will grow a lot and will become comparable to this one. So this is the result at a glance. In blue is with the assumption of flatness. In black, without the assumption of flatness, there's not much difference there. And as I say, without H naught or the clocks, only the combination RS. H is constrained. The moment you add some low redshift anchor, then you get the full measurement. So in a nutshell, it is possible to measure the standard ruler from low redshift observation in a model-independent way without making any assumption about gravity, GR, dark energy, or early time physics. The value measured is in agreement with the CMB lambda CDM, except for the combination supernova BAO H naught, as we were expecting. The error bars are still an order of magnitude larger than that of the CMB in fair value in a lambda CDM model. The error bar, however, slightly smaller than the CMB in fair one for a model where you add, when you mess around with the early time expansion history of the universe, like when you add a number of effective neutrino species as the parameter. And so you can use to constrain the number of effective neutrino species this way. The errors are dominated by the error on H naught. So better BAOs will not beat down the error that much. Better supernova will not beat down the error that much. Will beat down the error a lot. Will be a smaller error on H naught. So in the rest of the time that I have, I'm going to go back to the thing that I left suspended, which is how can you measure quantity, say early time quantity from the cosmological background data that are robust to the assumption about the late time physics. So what's behind trying to do something like this? It's because we believe that we are somehow mixing apple with oranges, right? The kind of physics that go on and we don't understand a late time, like the effect of dark energy, it's completely different from the kind of physics we want to explore or we believe we know or don't know in the early time universe. And we believe we understand better the early time universe physics because it's much simpler. But even in this case, this doesn't mean we should not test whether there is some room for freedom there. So that's what we set up to do. So can we constrain the standardized and radiation DAG from the cosmological background independent from late time physics assumption? And even beyond, can we just get some parameters of some physical quantity in a way that is independent about the late time universe assumption? And so this is in this paper, Early Cosmology Constraint, and the approach is based on an idea by Odren, Julian Lesgorsk, and collaborators in 2012. So the late time effect in the cosmological background are combined with the early time effect. What do we have? First, the position of the peak depends on the geometry and for the expansion history, because it's just you're seeing a standard ruler and it's subtend an angle, so it depends on the distance. So moving the peaks this way and this way, it's the geometry. Also, the overall amplitude of the high multiple, depends on the combination. Yes, AS is the amplitude of the initial perturbation, which is a primordial quantity, but then it also depends on the integrated optical depth to the last scattering surface, which is a late time quantity, and the combination come in this way. And there's no way to disentangle these two unless you look at low redshift and polarization. Now, at high L here, then there is an effect of smoothing of the acoustic peaks due to lengthening, due to the fact that there are structure in front of you that lengthens the CMB light, and the effect here is just to smooth the peaks out. At large scales, here you have the integrated Sachs-Wolf effect. So the fact that the photons that travel to potential wells see that the potential well changes, and it's different from when they enter to when they get out, and that creates some correlation with the and some extra power in the larger scales, and that depends on late time physics as well. So how do we disentangle the two things? Oh well, first, the effect of the geometry, it's like an accordion. It just moves all the high L above 30 or so this way. So you can cancel it completely by doing this change. Your CLTT goes into CTT, but beta L. So L equal 100 could be 200, 300, but L equal 101 could be 202 or 303. And the same for all the L. So if you marginalize over this parameter, you get rid of all the effect of the geometry and the expansion history between you and the last scattering surface. So this we get rid of. The integrated Sachs-Wolf, it's a little bit trickier. So we know it comes in at low L. So what we do, we just neglect the low L. We just cut at L equal 30. All the L below that, we just throw them out of the window. We'll see this procedure will have some limitation. And finally, there is the effect of lengthening. So this is the lengthening potential. And the idea is to say, okay, my lengthening potential, I just parameterize as an amplitude and a slope. And then I will just marginalize over both this amplitude and this slope. And that works amazingly well in taking away the lengthening information, both from the 4-point function, which anyway you can take off just by not considering the point function, and from the CLs. So if you do this, you can analyze the CMB data so that the late time information is removed. Now there is a star there because I want to come back to that. So we consider the standard lambda CDM 6-parameter model. A dark energy fluid, it's a perfect fluid. W, it's negative, and the sound speed is 1. A lambda CDM, but not flat. Recall that the CMB constraints on flatness come from late time effects. So this allows quite a lot of freedom to the early time components. And then 3 neutrinos, but with the perturbations that can behave differently from those of neutrinos. And then a case for some extra fluid, which equation of state is between matter and radiation. And in this case, the dark energy fluid, the equation of state parameter can go even below -1. So it doesn't necessarily need, we can cross the famous or infamous phantom device. So out of this procedure, we find that everything works extremely well except the contribution from the integrated Sachs-Wolf. So when the late time dark energy becomes very important, let's say the equivalent of lambda today is above 0.8, then there is a contribution from the integrated Sachs-Wolf that goes up to L equal 100 or so. And if you throw away the L up to 100 or 200, then all the procedure I told you about fails, in the sense that there's no much information in the data to actually do the analysis in a model independent way. So what I would say that this procedure here, it's dark energy hardened. I can be used to find a dark energy hardened CMB prior, in the sense that for 0 dark energy is fine, for value of the cosmological constant that are a little bit bigger than what is the standard value in the lambda CDM model, it works. But for very, very, very large value of the of dark energy, it doesn't work. It's not completely independent on the low energy assumption. So we have some idea on how to get around this, but they have not implemented. But what I want to bring home is that now we can constrain the sound horizon radiation drag in a way that is robust to assumption about the late time universe. And these are the constraints here, and you will see that the model that has got very large error bar is the model where you mess around with the early time expansion history of the universe. But also note that there are very strong constraints on the Hubble parameter recombination. The Hubble parameter recombination, it's constrained spectacularly well, again, except in this case. The summary of the story is that there's no much room for any of these extra crazy things that you can try to put in. So the early time physics, there's no evidence for anything extra, and the constraints are tiny on these extra components. So let me go towards the conclusion. This is a way to sort of summarize everything we discussed so far. This is the sound horizon radiation drag. This is the Hubble parameter measuring several different ways. This is the direct measurement. This is the measurement of the standard ruler. Remember, the standard ruler, if you don't use H0 or the CMB, will tell you RS time H, so it will give you like that. And then you can decide how to break this degeneracy, whether you use a high redshift anchor, and then you get this constraint, or whether you use the low redshift anchor, and then you get these constraints, and you will cut this line either down here or down there. And that's, again, the mismatch between cutting this RSH here or there. And so this is, for those who has been in cosmology for more than 70 years, reminds you of something. In 1999, there was a famous paper called the Cosmic Triangle. Remember? That it was the first paper that was saying, if we put together all the observation we have, it says that the universe looks like it's flat because the cosmic background, the large scale structure, and then we need a cosmological constant, and it was called the Cosmic Triangle. So here, this looks a lot like a cosmic triangle if I simply do one of these triad plot. So when, in the original cosmic triangle, it was a relation that was saying omega matter plus omega lambda is equal to 1. And while here you says that it says RS times H0 should give you something that is proportional, take away factor of 100 kilometers per second per megaparsec, the RSH you find from the distance, the low redshift standard ruler. And so you get another cosmic triangle, but in the log, because you have multiplication and not addition. And this is the cosmic triangle plot at 1 sigma, and this is at 2 sigma. So what this is telling you is that if you do the analysis in a model independent way, at the 1 sigma there's no agreement, at the 2 sigma the things cross. So if you do the analysis in a model-dependent way, you have the famous 3.4 sigma tension between Adams' measurement of H0 and Planck measurement of H0. The moment you go model-independent, the error bar grow, but this is powerful, because now you've done it in a model-independent way, or at least you know where the thing can fail. So I think I should conclude, so let me go to the conclusions. And then I leave the question of the void up for a discussion. So systematic errors are not only in the measurement, but also in their interpretation. And in this case, I discussed the adopted underlying model. And cosmology is quite special in this, in the sense that we have a model almost in anything we do. Even when we take a galaxy survey and we transform the redshift into distances to compute a power spectrum, we already assume a model there. It will be good to have a principal framework to deal with systematic errors. All of them. Now we don't have that. This is for another time. I've concentrated on the difference between constraining model parameters and understanding, and I'll show you some example and some attempt of being model independent and some possible approaches. And I should stop here. Thank you.
Thank you very much. Very nice talk. So shall we take some questions? Paco?
Could you comment on two aspects regarding H0? One is a work from Rigaud and collaborators, I think, I believe, including Sol Perlmutter, whether environmental effects seem to have an impact on the distances and on H0 of about 3%, I think they quote. And then second, on cosmic flows, which could produce some divergence. In particular, we found a divergent region around Virgo, which could have an impact of about 2% on H0.
Okay, so I know there have been direct discussion between the two groups. I mean, they've met and they've discussed, and they've agreed to disagree. So I think the jury is still there. There is the other issue of I don't know if this is related to the flows. There's another possible way to change the interpretation of the local H0 measurement. We say, we are in a special region, maybe in a void, and therefore, exactly. Now, in order to shift the H0 that as much to find complete agreement with Planck, you will need a void that is far too big and so unlikely in a lambda CDM model that you would have to throw the lambda CDM model out of the window anyway. And also the KSZ will be far too large, and we don't see that. Now, of course, there could be, half a sigma here, another half a sigma there, another half a sigma there, and they could all add together. But in this case, we are saying just moving H0 due to perturbation due to the local density. So in the RIS H0 measurement, they do correction due to the local flows, but they do correction out to 300 megaparsec. Now, if there is something that is beyond 300 megaparsecs that is big enough to actually change it by, say, 2 sigma, then that could be, but at least up to 300 megaparsec, they do have the velocity field and they do correct for that. It's like in a footnote somewhere, and then you have to actually go and tell him, did you do that? And he just say, yeah, of course, we've been doing it since, the first measurement of H0. I don't know if this answers your question.
I believe they're using local reconstructions with linear theory by Enzo Branchini. We have, I believe so.
I think they use the one from the group in outside Toronto.
Ah, you mean Hudson?
Yeah.
Mike Hudson. Okay.
They use those.
Well, we did a study with a little bit more sophisticated and found a divergent flow around Virgo, which could have a 2% effect, which does not explain 7% deviation. But
do you know which direction it goes?
An outwards flow,
Okay.
because there is essentially a void region around Virgo.
Okay.
Which, yeah.
So does this have anything to do with the paper that came out in Nature Astronomy yesterday about the repelling void or something?
It's kind of the similar work.
Okay.
Yeah. Actually, we had some
Discussion.
oh well, we had a common paper with Yehuda
Okay.
Hoffman on that reconstruction.
Juan, you have a question?
Not to belittle the throwing away of lambda CDM yet one more time, and its probably, as Dick Bond once said, the theory that's been most falsified, because it makes, he would say, predictions which the other ones don't. I have a question with the Rees paper, and your rules were not to question the paper and take them at face value, but I cannot understand why Gaia can possibly matter. And the reason is that the whole thing is anchored by the Maser distance to NGC 4258.
No, this is one of the three
Well,
anchors.
they have to make it, because that's the one model independent distance we have.
So,
I would,
so what they do, they use the three anchors, and then they show you
yeah.
result for all three anchors.
Sure,
So
sure,
you're
fine.
saying that you believe the Maser one, or you say you want to throw the Masers out?
No, there's no way around that Maser distance. I mean, it's a Keplerian
Yes.
overdetermined system, and so the distance to that thing is measured, and that's that. And as a matter of fact, when the Hubble Key project had a disagreement with it, they just changed the distance modulus to the Large Magellanic Cloud and made it agree.
Yes.
So my question would be that I would think that the weak point would be, where is NGC 4258 located with respect to the center of the Virgo cluster? And so that to me would be the uncertainty that we have. Gaia can possibly matter in that. And so I was confused by that.
Okay, so
and I would say if a second such Maser distance is measured to a different thing, then a lot of these things just go out the window. Right?
Okay, so Gaia enters because they use three different anchors. Among them, there are the Milky Way Cepheids. And the Milky Way Cepheids need some parallax. So the way they measure that parallax was to basically make the HST scan align with the way their CCD reads the charge to have a much better point spread function. That is like, pushing the HST to the limit. When the Gaia came out with the parallaxes on the same object, they checked that the parallaxes they got by doing this trick was actually correct. And so that anchor has been confirmed. The thing of the Masers, I agree, it's amazing, because basically you are doing geometric measurement, parallax measurement, but at a cosmological distances. However, if you look into the details, it depends a lot on how you model the Masers' circular velocities, and there's some modeling assumption there of how you basically model the geometry of the Masers itself. But you still need a model, it's warp, is not warped, is it always the same bit of the disk that lights up or not? So there are some, it will be good to have more of those. If there's more of those and they just give you the same.
Given that we don't know where NGC 4258 is located with respect to the center of the Virgo cluster, that would be the main uncertainty. You can move it a little bit closer than the average of the Virgo cluster, a little bit further away, and that's where your uncertainty is.
But you don't need that, because you have a redshift, and then you have a ruler because you know the geometry of your Masers, and then you measure the distance, and you have a redshift distance relation. That's all you need. So you're worrying about the peculiar velocity of that Maser?
Well,
but it's a cosmological distance, so at that point that correction is small.
because
it's not
you don't just take all the other systems, throw them away, and
Right.
measure the CFITs and NGC 4258, and that's the whole scale. Small number statistics, you actually end up
right.
using all the steps and the Virgo cluster.
Right.
So to me, the question is, where is that located with respect to the average of the Virgo cluster? And that's the limiting factor, not the parallaxes that Gaia measures. I
Right.
simply cannot see how that can possibly matter to that level, right?
So the three anchors give you more or less the same error into H0. So verifying one of them. I mean, you may say I want to throw that out and keep another one. That's fine.
No, I'm just saying one of these days somebody will find a second Maser disk
Yes.
at 3 or 5
Well,
times the
they're
distance,
actively searching
and-
for
and all
those.
these other arguments will go out the window.
Yes, they're actively searching for those. There's an effort going on, and if we find others, then it's just, you don't need to do a distance ladder anymore. You just do parallaxes at cosmological distances. That's it.
Are there any other questions? Okay, so let's then stop here, and thanks, Licia, again.